the curve has the equation y is equals to x squared minus 1 divided by x squared plus 1, where we have everything that we have here raised to power 4. In part A, we are supposed to show that dy dx can be written as ax into x squared minus 1 cubed divided by x squared plus 1 raised to power 5, where a is a positive integer yet to be found. Now, in this particular kind of question, we're going to use chain rule in order to work it out. And for us to start working out this question, we are going to use chain rule in this aspect that we are going to say dy dx is going to be equals to, we are going to take the power down, and this is going to be 4 into bracket x squared minus 1 divided by x squared plus 1 raised to power 3, because once you take the power down, you decrease it by 1. Then the next part is we are going to now differentiate what is inside the bracket. And something that you need to remember, whatever that is inside the bracket is basically two functions which are divided. So whatever that is inside the bracket, let me just work it out separately here. This is going to be what? Let me just work it somewhere here. Inside the bracket, we are having a function which is, let me just say, x squared minus 1 over x squared plus 1. These are two functions which are divided. So remember, using quotient rule, if you have u over v, then it means maybe if you are dividing dy dx is equals to u over v, that is going to be equals to v du dx minus u dv dx divided by v squared. This is a quotient rule method of differentiation. And so for us to work out this, in this case, we're going to say our u is equivalent to x squared minus 1, and our v is going to be equivalent to x squared plus 1. So du dx is going to be 2x, and dv dx is going to be equals to 2x. Now with this, we can be able to substitute it into this formula that we are having at this particular point here, and this is going to be v. Our v is x squared plus 1, we close the bracket like that, times du dx. Du dx is this part, so we shall have it 2x at this point, minus 1. Yeah, it should be x squared minus 1. I think I wrote this wrongly. X squared minus 1. So if we open the bracket, to be 2x cubed, this times this, it will be, because there's this minus, it will be negative 2x at that particular point. Yeah, so minus minus, it will be actually a positive there, and we shall have everything here written as x squared plus 1 raised to power 2. So at this point, you can see this part and this part will cancel out, so we shall end up having 2x plus 2x, that will become 4x over x squared plus 1 raised to power 2. So this is the expression we shall have after differentiating what's inside the bracket. So we shall transfer this part so that we can be able to write it here. Yeah, so remember, there is this part we were to multiply here is the differentiation of what's inside the bracket. So we shall transfer this value that we have here to this particular point here. So that will be 4x divided by x squared plus 1 raised to power 2. So which means that this expression can simplify to what? Can simplify to dy dx will be equals to 4 into x squared minus 1 raised to power 3 times 4x, this one here, divided by x squared plus 1 raised to power 3 into x squared plus 1 raised to power 2, which will mean that this equation finally will be 16x into bracket x squared minus 1 raised to power 3 divided by these terms that we have here, they are the same, so we add the powers, so it will be x squared plus 1 raised to power 5. So that is what this equation will become. And since the question was asking us to find the value of a is an integer to be found, so we can be able to say a is equals to 16. So basically that is our dy dx. Now once you have worked out that, show that the curve has a stationary point where x is equals to -1, x is equals to 0, and x is equals to 1. Now that's part B. Show that it has stationary point. The curve has a stationary point or stationary points at x is equals to -1, x is equals to 0, and x is equals to 1. So how do you show that a curve has stationary point? We need to remember at the stationary point dy dx is equals to 0. So which means that this particular equation that we are having here is the one that we are going to try to say is equals to 0. So we shall have 16x into x squared minus 1 power 3 over x squared plus 1 raised to power 5 is equals to 0. So if you take this part, you equate it to 0, or you multiply all through by 0, you're gonna get rid of the denominator, so which will mean that we were going to remain with 16x into x squared minus 1 power 3 is equals to 0. So which will mean we can say 16x is equals to 0. So if we divide by 16, we divide by 16, our x in that case will be equals to 0, which is one of the points that we are shown at this given point. The other answer is going to come from where we have x squared minus 1 raised to power 3 is equals to 0 as well. So we find cube root both sides. We are going to finding cube root. We are going to get x squared minus 1 is going to be equals to 0. Then we can now take the one on the other side. We shall have x squared is equals to 1. Then we find square root. We find square root as well. We can say x is equals to plus or minus 1. So x is equals to 1 or x is equals to -1 as also another stationary point. So that is what you are going to do in that particular question. Now use the first derivative to test to determine which two stationary points have the same nature and state whether they are maximum or minimum. Yeah, so that one you can be able to substitute. You shall substitute, and then once you substituted, you can be able to say, if we want to test, if you want to test the nature of the stationary point, for instance, if we want to test the nature of the stationary point for 0, it will have dy dx. At that case is going to be 0. So this is going to be, so dy dx is going to be 0 for when x is equals to 0. Then you can select a point just before this. So we can select maybe negative 0. We can select negative 0.5, and also here we select 0.5 in front of that. Then you substitute to check which answer is it going to give you. So for instance, let me just substitute to any of the equation that we have here. So see, the stationary point that we have at this point, our stationary point basically is this value that we have here. So we are going to substitute. I open the bracket, giving us a positive value, so the gradient will be like that, and also here it will go flat because that's the stationary point. So we are going to check now for this one. So this is going to be times 0.5 times, so we are just inputting it here, 1.1. so this one is negative value, so the gradient is going to go like that. So which means that 0 is a maximum point. X is equals to 0 is a maximum point. Yeah, but what was the question asking us? Use the first derivative to determine which two stationary points have the same nature and state whether they are maximum or minimum. Maximum or minimum. Yeah, so you're gonna try the same. You'll try the same the way we've just done here. You also draw a table for x is equals to 1 and x is equals to 2. X is equals to that. So let's just try it out. I'll have my table into brackets 1.5 raised to power 2 minus 1, close the bracket, raised to power 3, so divide by answer, which is going to be positive. This is going to be positive, so meaning this graph will go like that, then so this is a minimum point. After trying for x is equals to 0, this is a maximum point. X is equals to 1 is giving us a minimum point. Now if you try for x is equals to -1, you are going to say x -1 is dy dx is 0, so this is a flat. Then if you select a point after -1, for instance -1.5, it's going to give you a negative gradient, or you shall get dy dx is a negative number. Here if you substitute to this part, is going to give you 0, and for a number in front of -1, for instance -0.5, is going to give you a positive number, so the gradient will be like that. So this is a minimum point. x is equals to 1 is a minimum point, and x is equals to -1 is also a minimum point. So we can be able to say x is equals to 1 and x equals to -1, both are minimum points. Both are minimum points. So that's how you are to conclude in this particular question. The nature of those 2 points are both minimum points.